干嘛搬走？都搬走啊？做什么东西？
就是说他不要放，他这边。这是某月左右后面去啊，派人把我绑上来去。
Plus. Something. Let's say you was a culture. Example.现在开始，对，现在就是对，一定要这边去多地也是，不好意思，这不是写这里写了，这一天算命的，但是呢，考试也不一样快。啊，哎，哎，要是，你跟学校说，再跟我说，跟学校说啊，没有，比那个日期前28号，而且哦，这 Did you hand in your project to the Turnitin? Huh? But how you obtain your Turnitin report? Huh? Online shopping. Oh, I mean, you hand in to our Turnitin system also. Can you hand in? Do you know we have a account for the assignment? Yeah, turn in there to have a record. Okay, yeah. I think you should be able to submit. You just submit there so that I have a record. Yeah, sure, sure. Yeah, you try to submit. If cannot, let me know. Yeah. Wow, why on time, huh? 2 o'clock. Huh? Why not 30 today? Should we talk about assessment first, or should we start class first? Later we talk about assessment. Ah, assessment first. Okay. So, the remaining assessment. Okay. So let's deal with the admin stuff first. If you already browsed through our Moodle, right, I've updated the course information and assignment 3 I posted up today. There's no solution, right? I scared I post out the wrong version. No, I mean assignment solution. Right. So yeah. So let's talk about assignment. So assignment 3 is our last assignment. Okay. Um, I have a planning for the deadline. So this deadline, hopefully we don't move it anymore, right? Okay. After the line, you are dead. Okay. So this is the deadline. Okay. So the first deadline is the 21st March. So I give you about 2 weeks to do it. If you can't do it, you should get help from me or the rest. So this is the assignment 3 deadline. I think you should start looking at it now. Okay, it's not. It's okay that you cannot solve today, but you should let the question sink in to your mind. Okay. So first deadline is 21st of July. June, sorry, 21st of June for assignment 1. And project 2 and project 2 should due on 29th of June. Okay. So we try to finish everything before July so that you can study. Okay. Let's finish everything before July. Uh, but the talk will happen before the project due. Okay. So meaning after the talk, if there's something you want to adjust, you can adjust. Okay. So the talk will be happen on the 28th. I think I want to do it during the class time. So it's this period here. Okay. During the class time. I'm not sure. I wonder if I want to like invite others to come. For example, invite AIT students. Yeah. So tell them. So later I will tell you what we have to do in that project. Okay. So I put a box on these 2 Sunday, right? So these 2 Sunday you can start sending in draft already. Okay, draft for project. Okay. Or even this week you want to start sending in also can. Yeah. Okay, some of you already have ideas, so you can send it to me. Yeah. Wait, I haven't thought yet. Patient, I will tell you. Okay, I'll tell you soon. Okay, so this is the deadline. Okay, I'll tell you what's the content you need to do. Okay, so assignment 3 is the usual max assignment. So it's posted. You can have a look. And about project 2, right? Okay, so the title is real life application to mathematical theory. Okay, like last time what we discussed.
So the content without reference should occupy at least half of a page. Okay, half to one page enough. Okay, don't do too much. Just half or one page. So similarly, talk to me and discuss with me before writing. So during this project, right, some of you didn't talk to me and you decide very late. I cannot give much suggestion. So yeah. So please talk to me before you decide what you write. Okay, so the aim of the project is the same, but I changed the third point here. So one of the aim is to find the real values of doing maths. So project recommendation, I list out some using my own knowledge. For example, Fourier series in sound technology, I think they use Fourier series. For example, Apple AirPod noise cancelling. Again, you can try that. Or if you like physics, Ramanujan summation in quantum physics, maybe deal with some boson fermion statistic. And I think there's double integral in statistic, right? Some high dimensional probability maybe, or join, what's the word? Join probability, join cumulative probability, or what? Hey, what you guys learn? Is it? Okay. Okay. And continuity in image processing. For example, GoPro hyper smooth image stabilization. Are they using continuity or not inside their technology? Or calculus in astronomy, if you like to play around with orbit, how orbit of Mercury, three body problems. Yeah, three body problems. Okay. Fibonacci sequence in arts. Okay, for example, Mona Lisa, why it looks so nice. Okay, yeah. If you have some literature also can, some rhyme also can, rhyme in sequence literature, like poems, Chinese poems, or something like that, also work. Okay, as long as you find connection to calculus too. And Pythagoras theorem in architecture, for example, Egypt, the Great Pyramid, why they make a great pyramid, how is it so accurate? Okay, so these are just some suggestions you can find yourself. So project structure is, because just only half page to one, so very easy. Tell me what's the problem you want to solve, problem statement, short and precise, and solution. Okay, what's theory you use, how to solve the problem, that's all. And if you have used any reference, or please cite it. Yeah, please cite it. So marking criteria is similar. So based on your English, based on your completeness, logic, based on your difficulty. So in project one, right, some of you pick very hard topic, but you can't manage it in the end. Okay, so it's kind of a waste. And you don't approach me at first. Okay. So please, you need to measure your own ability. Okay. Yeah. This is part of your life. Okay, second part is this presentation. So presentation topic is, why do we do maths? Okay, this is a frequent topic asked by, I guess, your friend, right? Do you encounter this or not? Your friend asks you why you study maths. Or you study maths, you should know how to calculate, right? Okay, so why do we do maths? Okay, so the talk length is about 1 minute, enough. Okay, just 1 minute. I don't want you to talk bullshit a lot. Okay, just 1 minute. Keep short and sweet. Okay. 1 minute, extra time 0.5 minutes. So on that time, I will need one timer help me. Okay, like the debate, debate competition. Ding, ding, ding. Okay, so force you count down. 1 minute primer presentation. So about maybe 1 slide, 2 slide, 3 slide. That's all. 1 slide also enough if it is concise. Plus, very important Q&A section. We'll have 1.5 minutes of Q&A section. Okay. So this Q&A section, right? I can ask. Everyone else also can ask. Okay. We will take about 1 or 2 questions. So if you ask question, but not on your presentation, right? You can earn extra mark if you ask good question. Okay. Yeah. So to earn extra marks here, ask a good question to your colleagues during any Q&A section. Okay. Everyone can ask. Okay. So the top content is present your project to in a creative and informative way. Okay, creative and informative, both. Okay. I don't want creative but no content. Okay. I don't want full of content but boring. Okay, creative and informative, both. And then one key question you need to answer at the end of your talk is why you first choose to study maths. Okay, this is the first question I throw to you at the start of semester. I know that maybe some of you already choose not to do maths later on, but tell me, why is your first love? Okay, why you choose to come to do maths at first? Okay, so this part here, right? I don't want fancy word, don't want fancy language or uh, fake, fake reason. I want you to be honest and sincere. Okay, honest and sincere, you'll get high mark. Okay? Honest and sincere. So try and think how this question integrate into your project. Okay. If not, you answer it in the Q&A section also. But try and see if you can integrate this section into your project too. And some marking criteria, I think we only have 5% left. So about 2 to 1. So 2 for language, 2 for your completeness, 1 for your flexibility. So I want to see your on-the-spot reaction. Yeah, like people throw some question on you. So how you understand, how you handle. Okay, how you handle the on-the-spot situation. Okay, maybe technology problem or anything. Okay, yeah. Okay, like a bit like interview. Yeah. Okay. So I mean, I plan to invite AIT students for this one. So let them appreciate why we do maths. And maybe you also can invite your friend to come. Invite a friend to come. Okay. I will think about it and then I will ask about their idea. And then if we do it large, then we see if we can find large space and then I borrow more microphone. Okay. Make it an event. Yeah. Yeah, event. Ah? I mean, just make it a seminar stuff. Okay. I'll see first. I'm not sure yet. I'm just an idea. Okay. But what's your job? Your job is to find the reason of why you do maths. Okay. Find the reason why you do maths. So this project, the topic you find should be interested for you. Okay. Because you're interested in this one, and then you see beauty of maths in this area, and then you share it to the rest. Okay. So the whole idea is share to others. Okay, share to others. And this idea instills since the project one. Okay, what you wrote, what you say is to share to everyone. Okay, share to everyone. Okay, any question you want to ask about deadline, about content, about how we assess it? We can add detail if you have questions. Any questions? Does anyone clear what we need to do? Okay, please read the document. If you don't understand the document, you should ask me as well. How long must be the project too? So I put it here already, project length. So about half to 1 page. At least half, and then up to 1 page is enough.
So,
yeah. No, it's okay. You can do with reference. If you do with reference, you just write down your reference.
So that means that 1 page, the half content we must be. The other half.
Yeah. Content without reference can just be what half page. So the question should be simple. Okay, you need to do it simple, but how to say? You need to explain it simple, but it is what should I say? But any idea?
So, so how
Yeah.
is the solution must be given in this project?
What do you mean?
Is that, for example, set a question and then solve it, or
No. You give your problem, right? So for example, Apple want to make a make a earphone with noise cancelling, for example, like that. So how we do that? So they create another voice to cancel out the surrounding voice. So make you think that you listen to nothing. For example.
so just use the word and some mathematical term to describe.
You mean for solution?
Yeah.
Yeah.
No, just full of word and
Yeah, definitely. Yeah. I thought this is what you do in my class. Yeah, use word. Yeah. If you need equation, of course you write down the equation. But yeah. 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 Any more questions? Yeah.
how we apply them.
Let me think. Should we recall the theory you use? Should we recall the background, the knowledge background?
Don't need to give you like how I calculate all of it. I only need to tell you like what I did to get.
You don't need to tell me the whole story, okay? But if the definition is required to explain something, you give the definition. If not, take it as everything we know. For example, Fourier series, you don't need to say what is the definition of the Fourier series already here. So you just say that how we manipulate this, and then unless the definition is really important to explain the thing. I mean, you use the thing that we have introduced in our class, so we don't need new definition. Again, maybe for example, Conso, right? Conso have an idea of using fast Fourier transform. Okay, maybe it's not too well known to the rest, so maybe say about few words about fast Fourier transform. Maybe not informal. Okay, just say what it does. I mean, say until the stage that you can use it. People will know what you're trying to do. Okay, not need to be too formal. A series is a function, is a sum of function or you just say, it's a linear combination of cosine and sine wave. That's all. And you don't need to tell, what's the coefficient lies in R, is that CM? Is that not it? Yeah. This, yeah.
Can you make it application in many kind of way? For example, a theory, then apply it in some different field, and then all the field will talk about how this theory is applied.
Or you want to make it my idea is you pick a specific field and then I said it's too long. Maybe you can bring it out in the Beamer talk. Or I don't want it to be too much. Don't do it too much. Do it in a specific case. Let people see, this really works. Where is the point? Okay. If you want to talk about in Beamer talk, or we also can apply in the others. You also can. Yeah. So I mean, you guys spend a lot of time in doing projects, right? Okay, so spend it efficiently. So to spend it efficiently, you need to know what we need to do. Okay, any more questions on projects? Yeah. Beamer also make you, yeah, Beamer also use latex. I don't have a Beamer template, I think, but you can just search it Google. I think there's a lot of Beamer template on the Google. You just download it, then you can use it. Yeah. More question or not? More? Okay, everyone okay? If you're okay, then we have to start running right here. Yeah, run to the end. Okay, so remember these three deadline, they form a triangle. Again, yeah. So project and presentation Beamer will be submitted after the talk. Okay, so after the talk, you still want to change anything, change it. Similarly, we will have turn it in and then cover page. Okay, similarly. Yeah.
If Wednesday enough for all the students.
About 3 minutes, so I adjust. So 3 times about 44 and 44 people here. So calculate 132 around 132. I think should be more than enough, right? 132. We got 3 hours.
I think not enough.
You think not enough?
But we have some
I mean, we have around maybe 50 minutes of leverage. I mean, we have 3 hours class, right? About 2 minutes is for presentation. So I think we still have some room. If not, maybe we can start earlier also. Because this class, I think, doesn't have. Yeah, we can start earlier also. If we start earlier, finish earlier also can, right? Yeah, start earlier, finish. So yeah, I mean the details when the time comes close, we will decide. Okay, yeah, we will decide. Is it okay? So I mean the date should be today, no? I mean on the Wednesday, one of your class. It's 28. And the venue and the time later we can decide again. We fix 2 to 5 first. Okay. Any more concern? Any more concern? Or what? Calculus 2. Could be calculus 2 apply in statistics and finance, economics. Yeah. I don't want to do maths anymore. Don't want to do maths anymore. Do it in other field. You need to describe it as a real world problem. For example, projectile motion. Projectile motion, sometimes you do the calculation on the missile, right? Missile. So you write it as a maybe World War II, World War One, any one of the war, okay? And then you want to destroy the city. So how should you place your what angle you need to put to destroy the okay, maybe you're right. Okay, but don't want to say sensitive later. Okay. Yeah. Anything? Like you can discuss why Russian cannot invade. Is it something wrong with the angle shooting or not? Okay. Yeah. What else? Okay. Or maybe you discuss why US why need to increase what? Increase the upper limit of the what they call it? Upper limit of the. Do you guys see news or not? No, don't see news. US increased the upper limit of economy. not bank interest, right? It's the what's the word?
Taxation.
Taxation. Eh? It's like they borrow money, like they reach the upper limit already, so they increase the upper limit, so they can pass the budget and then give the give give stipend to the government. So yeah, so maybe you can discuss why they need to keep increasing the upper limit, why we cannot reduce it. Maybe there's a derivative inside there they cannot handle. What? If you want, can inside my class can. Inside my class can talk about sensitivity. Okay. Okay. Anything else? Everyone clear already with the project? So if you want to keep referring to the what you need to do, so keep referring to Moodle. Shermaine, you know what we need to do? Check Moodle. If not, ask me. Okay, if don't understand, ask me. Check Moodle. Always check the Moodle. Course information. All right. Okay. So we start the class. So have you guys know the exam time yet? Not yet, huh? Once you know, you let me know. Kind of. Yeah. So once you know, let me know. Okay. Yeah, we are here. Okay. So okay. So let's return to let's recall what we did last time. So the first thing we do is if f is continuous, f is a function of two variables, is continuous on R, then it is integrable on R. So Ziqian says something about this theorem here. So before it, we say that f is bounded on a closed rectangle R and it is continuous there as set on a finite number of smooth curves, then f is integrable. Okay. So this condition here require bounded, so you won't have something not continuous and shoot to infinity. Okay, so you don't need to worry about that case. So that case is similar to fx equals to 1 over x. Okay, so this is a place where x is not continuous at 0. It is also not defined at 0. Okay, not defined at 0 and not continuous at 0. So this, I mean, do you know that any function, one variable function can be extended to two variable function just by keeping another function running? Okay, so instead getting one line, you get a surface, you get a surface that pressed up by the line. Can you imagine what is that? Okay, let me draw something. So at first, you only have 1 over x, right? Okay, if you add another dimension, so you will trace out a surface because at every y you have this line here. Then you got a surface. Okay, so this is this is part of the string theory. Okay, string theory also work like this. So how you get a line? Okay, it's because a dot moving. Okay, so how do you get a surface? You trace the surface by the line. And then how you get a solid, 3D solid? You trace out by the surfaces. Okay, the surface move, then trace out a 3D object, and then so on. So these are called the membrane, D-brane inside the string theory. Okay, D-brane is dimension 1 brane, 2 brane, 3 brane. Okay. Yeah. So the two condition here, bounded and not continuous at finitely many smooth. Okay. Yeah. Second thing is about this Fubini's. So Fubini's theorems, right? We not just dealing with rectangle domain. Okay, f has to be continuous on this rectangle domain. Okay, this is the version that we are given in the textbook. So Fubini's theorem, right? Later on in the later year course, you will prove it. Okay, you will prove it in a more general setting. So first here, I want you to appreciate what this Fubini's theorem is doing. It is not just changing the order. Okay, it changed the way how you integrate the surface. Okay, so for example, if you look at this order dx dy, right? Okay, so it tells you that you need to fix a y and then integrate over x. Okay, so for example, in this picture here, let's say this is your f, the blue part is your f, right? Okay, so you fix a y, okay, you need to integrate over the x axis. Okay, so in your mind, right? Okay, in the chapter of no matter is derivative or integrable integration, you need to split your axis. It's a good idea to split your axis. Okay, so you look at x-axis, how does it look like? And then you look at y-axis, how does it look like? I mean the cross section. Okay, cross section at x-axis and at y-axis. So for example, right? For example, in this case here, okay, we differentiate dx first and then differentiate dy. Okay, meaning what? Meaning that, okay, so let's use an example, right? Let's use an example. Okay, let's look at this example here. So last time we evaluated this integral. Okay, does anyone know what we are doing here? What are we actually doing here? So you can see that this y here, right, is changing with respect to x. Okay, the y here is changing with respect to x. So meaning at 3, okay, you are integrate from -3 to 3 squared, okay, which is -3 to 9. Okay, so this part is 9. Okay, so for y equals to 3, sorry, x equals to 3, you are integrate over this line here. Okay, and then if you keep going 3.1, or let's say 4, okay, let's say 4, s equals to 3, y is going from -3 to 9. When s equals to 4, y is going from -4 to 16. Okay, so it's going from -4, for example, to 16. Okay. Okay. So what you do is you fix a value at x. Okay, integrate over the y. Okay. So at the last step, you need to add all the x value, right? Okay, because in the inner part of this integral, you only integrate over y. Okay, you only integrate over every pieces. Okay, so where's the calculation? So this calculation here tells you what happened to every pieces. Okay, all right. So if you sub 1x inside here, you get a number, right? Okay, this tells you what happened to the single slice here. And then finally, you integrate over the whole interval of x that you want to integrate over. So you add up all the slices so that all together you get the area you want, the integration domain you want. Okay, so far okay. So this is 2D. Later we need to imagine 3D. Okay, so this idea is kind of important. So later when we integrate over one point, right? Maybe you have a whole surface you need to integrate over. Okay, now it's just line. Okay, so far okay. Question? Any question? Any question? So does it make sense like why the inner part is depending on the outer part? Does it make sense? Why the inner part is depending on the outer part? For this case, I mean, because over x, your y changes. Okay. So when you integrate the inner part, it tells you what happened at every x. Okay. And finally, you need to integrate over the whole area. So you need to add up all the cross section. Okay. Okay. Question? Don't be shy. Okay, so as what I said last time, right? When you look at this notation here, so let me bring this notation now. I roughly say that this is like a partial derivative where you treat the other variable that you don't integrate over as a constant. This is the definition. This is the actual definition from the textbook. Okay. So how you view this? How you view this inside your Fubini's theorem? You see, there's x and y inside your function, but you only integrate over y. Okay, so what's this thing here? Okay, we never see this thing before. So this is actually called a partial integration with respect to y. Okay, so you really treat the variable that you don't integrate over as a constant. Okay, that's all. I just want to make this precise. Okay, yeah, this is one of the questions pointed out by Ming Xiu last week. Yeah, we should put this in to fill in the logic. Okay. Okay. So it's really like a partial, I mean, and partial antiderivative. Okay. Anti of derivative. Any question? These are the gap we fill in last week. If no question, then I need to make you do question or okay. No question? No question. So let's try this. Spend few minutes, try and compute this. Sometimes right, I make you to start from scratch, right? So this is one of the skill that math students should have. You need to know where to start. Try and see if you can find the integration domain or not. There are two ways to solve this. Maybe one is trickier than the other. It's one linking here. Okay.谢宜州。杨柳青。Okay. Think you should at least get the integration domain if you haven't finished calculating. Anyone finish calculating or not? Finish. Simple finish. What do you get? Huh? 36. Kind of right. Okay, it's all right if you didn't finish, but let's start discussing first. Okay, see if you get the right integration domain or not. Okay, you can listen or you are calculating. So let's say we are not given these two diagram, right? So how to do it from scratch? So you need to know how to plot the area bounded by the line y equals to x minus 1 and xy squared equals to 2x plus 6. So y equals to x minus 1 should be a straight line, okay? It's the y equals to x shifted down by 1, okay? So you first draw the original basic graph, okay? And then you shift this graph down by 1, okay? How about y squared equals to 2x plus 6, okay? So this is not y equals to x squared basic graph, right? So this is the shifted one. When it is shifted, there are two versions, whether it is open to the left or open to the right. Okay, so this is open to the left or open to the right. Y square is always positive, right? So how? Can you get positive number from negative number? Or you don't understand my question? Can you get positive number out of some negative number? No, right? Okay. So you need to keep your x always positive. So it is open to the right. Okay. It's open to the right. Okay. So there's a bounded region here. Okay. So one side is y equals to x minus 1. The other side is y squared equals to 2x plus 6. Okay, so how to integrate over a region that's not rectangle? This region is not rectangle, right? Okay, so we need to use the theorem. Okay, we need to use the theorem. So this region is controlled by two curves here. Okay, controlled by two curves here. So there are really two ways to do it. Okay, one way is you fix your x and then integrate over y. Okay, second way is you fix your y and then integrate over x. Okay, depend which one you want to do. Maybe typically one way is easier than the other way. So you need to do more exercise to see it. Okay. So let's say you want to integrate over x. So let's say you want to find out the region of x it integrate over. So what's the region of x it integrate over? So you need to find the least x and the most x, the greatest x, such that this region lies. Okay. So the lowest x it lies is when y squared equals to 0, right? Is that right? Is it right? Right. Okay. So because it's the minimum point of y squared equals to 2x plus 6, right? Right. Agree? Anyone agree? Agree, yeah? Okay. So when y squared equals 0, x equals to minus 3. Okay. So how about the largest x for this bounded regions lines? It is when the two curves intersecting. Okay, so let them intersect and then see what's the x you get. So when x equals to x minus 1, substitute it into the other curve. So you solve this. So what do you get? What do you get? 6 and then x squared just 4x. Please help me check whether my calculation correct. Okay, so you get x minus n minus 5 better and x plus 1. Please check, check my solution. Okay, so you have x equals to 5 or x equals to minus 1. Okay, so you can notice that there are two intersections here. Okay, so meaning one of them is 5, one of them is minus 1. Okay, so this side is minus 3, the other side is 5. Okay, how about y? How about y? Okay, where do you integrate from? From which point to which point? So actually from the graph, you can see that the highest and the lowest point is actually the intersection point. Okay, so you just need to check at the intersection point, what are the y's? When x equals to 5, y equals to 4. S equals to -1, 5 equals to -2. Okay, so top and bottom you have, sorry, here I put, what am I doing? Oh, okay, so I leave out the x, y part. Okay, so here we have 4, at the bottom we have -2. Okay, so so what do you do next? What's the next thing you do? What's the next thing you do? So you want to do dy dx first or dx dy? How about I ask Pishon, what do you do? Do you do dx dy first or dy dx? Dx dy. Okay, sure. Let's do dx dy. Okay, so dx dy means what? You keep y fixed first or you keep x fixed first? Right, okay. So you keep y fixed first and then look at every y, what happened to the x? Okay, so we keep y fixed first, meaning we need to keep from -2 to 4. Okay, so when we look at every y, right? Okay, what happened to our x? Okay, at y equals to 4 is just 1 point. When you reduce going down to -2, you can see that this line changes based on our domain. Okay, and then how this cross section changes based on the two bound of our curve. Okay, on one side we have y squared equals to 2x plus 6. The other side we have x minus 1. Right? Okay. Okay, so how so how do you pick? How do you pick the dx? Dijon, how do you pick your dx? The integration domain for your x? You mean for x? For x? You mean for when? What's the answer? Yeah, I mean, what's the integration domain with respect to x? We already decide what's for y, right? -3 to 5. Okay, does it work? No, right? Because our y, you can see that our x is changing. You see, it is changing. It's not fixed. If you say it is -3 to 5, right, you will get a whole rectangle. Because for every y, you want -3 to 5, 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 until you go to -2 or -2 up to 4. Okay, depend on the order. So you get a whole rectangle. But we want the shape that changes based on the x. Okay, we want the changes based on the x. Okay, so what can you do? What do you know? Okay, so how y control the x? We also see from the curve here. Okay, let's see from this curve. When y equals to x minus 1, we know that s changes by y plus 1. Okay, how about on the other side? We know y squared equals to 2x plus 6. So how does x change? x equals to y squared minus 6 divided by 2. Okay, so meaning what? Meaning if you tell me a y, okay, you tell me a y, I know what is the x on the cross section. Okay, you believe or not? Let's try. Okay, let's try. Let's try what happened when y equals to 4. Okay, what happened when y is equal to 4? Let's call these two curve different name, x1 and x2. Okay, so when y equals to 4, what happened to x1? Hey, calculation quick. Y equals to 4, x1 equals to? Huh? 5, huh? How about x2? Wait, 4 plus 1 also needs so long. Okay, so you see, when y equals to 4, right, y equals to 4, x1 and x2 is both 5, so it is just 1 point. Okay, let's pick another one. How about pick any point we know, huh? So what's this line here? What's this point here? What's this point? Y equals 0, x equals to 1. So this point is 1. So let's see, when we fix y equals 0, what is this line here? What's this cross section here? Does it match up with the diagram here? Okay, so when y equals to 0, what is S1? S1. -3. Okay. How about S2? Huh? 1. Okay, see? So when y equals 0, you are integrating from -3 to 1, which is this cross section here. Okay, so you can see that the x here is bounded below by y squared minus 6 over 2 and bounded above by y plus 1. Okay, so this is your integration domain here. So on one side, it is half of y squared minus 3. On the other side, it's y plus 1. Okay, this also makes sense. Okay, see this integral here. This also makes sense. Okay, after you integrate over x, what you left is y variable, and then you integrate over y variable. Okay, this is how you check. Okay, make sense? Okay, huh? Okay, then the problem is you need to do this iterated integral. Okay, do this iterated integral. So when you want to do iterated integral, you need to treat the other variable as a constant. So in this case here, you treat y as a constant. So you should get y squared over 2 first, and then s equals to y plus 1, s equals to half y squared minus 3 of dy. Okay, and then you continue and do this integration, and then at the end you will get what Jimpo get is 36. Okay, yeah, you can continue the integral yourself, and then check that your answer is 36. I'll post out the solution later, but I'm still interested in discussing about this integration domain here. Does anyone of you did dy dx? Anyone did dy? Mingxiu did dy dx. Okay, so what do you do? Okay, we need to split, sure. Why do we need to split? Okay, first of all, okay, let everyone on page first. So let's say we want to differentiate dy dx. So meaning what? So you fix the outer variable first, okay, and then you look at the cross section. Okay, in this case is the vertical line. So you fix the x-axis first. So x-axis, where are we integrating from and until? Where? 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 Wait, slow, a bit slow. Where are we integrate from and until for x-axis? From where to where? -3 to 5. Okay. So when we go from -2 to 5, right? Okay, you look at an x value. How does this cross section change? Okay, so this cross section change based on our curve here. Okay, based on our curve here. Okay. So what do you mean by you want to split? Means you. Okay, this line. So you are talking about this line here. Okay. Across this line. Sure. Okay. So can you see that the y here is controlled by different curve. Okay. For the x less than -1 is controlled by a single curve. Okay, but when x greater than -1 is controlled by two curves. Okay. 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 So, but this curve here, right, is y squared equals to 2x plus 6. So how do you split into two parts? Are you integrating y 2x plus 6 to 2y plus 6 or not? Are you integrate from square root 2x plus 6 to 2x plus 6 or not? Are you doing this integral? Do you get what I mean? Do you get what I mean? So how do you find the integration domain for a single curve? Use positive square root and multiply by 2. Use square root okay, you can do that because in this case it's symmetric. You can do that in this case. You can integrate from 0 to square root 2x plus 6 and then multiply by 2 because it's symmetric in this case here. Okay, but in general, how to do? Okay, in general, you need to split this this integral here into two parts. Okay, bounded above by square root 2x plus 6 and bounded below by negative square root 2x plus 6. Okay. This is similar on how we split the sphere into the positive hemisphere and negative hemisphere. It's the same idea here. Okay. So the top part of this curve is described by y equals to square root 2x plus 6. The bottom part here is described by negative square root 2x plus 6. Okay. 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 So this is what happened when you integrate from -3 to 1. Okay. After 1, it is bounded below by x minus 1 as positive square root 2x plus 6. Okay. So you split this two part into two integrals. Square root 2x plus 6. The other one is minus square root 2x plus 6 to square root 2x plus 6 by dx. Okay. Any question? Oh. Okay. Understand. I mean, if you have any question, right, you just throw it up. Okay. Simple one also okay. Because others people might have the same problem. Any question before we break? Okay. So I mean, you should try both way and then see that you get 36 also. I think both integral is not hard to do, just that the integration domain is a bit trickier. Okay. So what? Yeah. No. Okay. Actually, this double integral doesn't represent any volume, right? Because xy is not always positive, I think. Xy is not always positive, so it doesn't represent any volume. Question? Yeah, question. Mm-hmm. Mm. Mm. Okay, sure. Okay, sure. So, why is this the lower limit for? Okay, so first of all, this upper limit and lower limit only work for x greater than 1, right? After x greater than 1, okay? So when x equals to 1, right, we are integrating over this cross section. This agree or not? Do you agree with this? Tivon, do you agree with this? Okay. Okay, so let's check this point here. Okay. This point here, does it given by x minus 1? Okay. So when, let me use different color. So when x equals to minus 1, y equals to x minus 1, which is minus 2. Okay. And the above, what do you get? We say that it's bounded by y equals to square root 2x plus 6, right? Okay. So when x equals to minus 1, this point is actually, what's this point? 2. Okay, good. Y equals to 2. Okay, so meaning this point is 2. So we are integrating from minus 2, okay, to 2. Okay. And then for example, when x equals 0, let's look at x equals 0, right? X equals 0, what happened? Y is equals to minus 1. Okay, so this suggests that this point should be minus 1. Okay. And then at the above, what do we get? We get square root 6. So here should be square root 6. Okay. Let's take another point, last point, the end point. Okay. If this is bounded below by this curve and bounded above by this curve, we should get a single point here. Okay. So let's say x equals to 5. What is y? 5 minus 1 is 4. Okay. Bounded above by this curve, square root y equals to square root 2x plus 6. What is this? Square root 10 plus 6, which is also 4. Okay. So the lowest point in this cross section, in this set of cross section, is bounded below by x minus 1 and bounded above by square root 2x plus 6. Is it clearer now? I mean, for every cases, you need to see this, okay, to make sure you do the right integration domain. Okay, so you, yeah. You saw the direction. Oh, you said the direction. Okay, yeah, sure. Yeah, so it's very important. So if you fix x first, then you integrate over the y cross section. If you fix y first, then you are integrating the x direction. Okay, so you need to see you do dy dx or dx dy. Okay, so the outer one fix the inner cross section. Make sense? Okay, because the inner change based on the outer variable. Okay. So this final exam, right? You are not allowed to bring cheat sheet. Okay. So if you don't bring cheat sheet, I will see. I need to prepare some theorem like that. Okay. Maybe similar to AIT one. Yeah. Okay. Definitely no. Definitely no. But will be easier. Will be easier based on lecture, not example for the calculation. Yeah. Okay. So for example, this kind of questionnaire, you need to understand it well. Yeah, I still believe. No, you need to keep believing. Okay. I mean, I didn't yeah. So what we discussed in lecture, right? Very important. It will be come out in the test. Okay. What? What is it? Directly print the lecturer side?
Yeah.
What do you mean?
This is a good. And then question just directly print from the
Oh,
It's easier for you, you don't need to pretend you.
maybe some of it is, but some of it not. Yeah. Some of it is. Yeah. Okay. Yeah. Yeah, I will let you see before you go to the test so you can know what to prepare, what not to prepare. Okay, let's break until 3:22. 3:22. Yeah. Mm. Mm. Yeah, because Beamer yeah, yeah. I think it's called the Beamer template. So I mean, because your final year project also need to use that. So actually, I never used before. So but the school here requires you use some. Because my school didn't teach me. So you learn it now. Yeah. Huh? What? I don't know. Oh, this is okay. I mean, make a simple one. No need to. Yeah. Make simple one. One slide also can. One slide. Huh? Yeah. At the end of the project. Yeah. At the end of the project. I didn't expect we will spend 1 hour in this example. Half hour? About half hour. A bit more.
Because you have a bit more doctors now.
Huh?
Because you have a 30 minutes.
Okay. Yeah.
People talk from 40 seconds.
Hopefully we can finish syllabus on time.
Not finish, even though exam deadline.
Then I need to tell you the answer already. You want to know when is Yiming? Go back holiday, huh? Go back holiday. Huh? Family issue. Okay. Sheldon lost for a long time ago. Around the world. Too busy. Jia. We got roommate here. Is it? Where's Jia? Ah? Uncomfortable, okay. So you cannot submit it. Let me see. Due date, post date. The due date is the time for it to due. Let me see. Allow submission after due date. Okay. I open this. Yeah, you try again. Yeah. Hopefully later we will have time to do the task assigned by your lecturer. Gaussian. The integral. And later we'll do the integral. Minus infinity to infinity of e to the minus x squared. So later we will do this. Okay, so later we'll do this meme. We'll do this. Do you guys understand this meme or not? Why you don't understand? Don't get it. Do you get it? Why is it easier? Why is it easier?
Because it's already have the pattern after the integration of the power, after the differentiation of the power.
You can do by part, right?
Yeah.
Yeah, but second one you cannot by part. Second one you cannot by part, right? I think can or not? Cannot, because you drop out the 2x. Or the other part. Oh, okay, we are okay. Yeah. Solution, yeah. Yeah, solution. Okay, I think we should start soon. Times and time, wait for Norman. Okay, so property of double integral. Okay, so like I said last time, right? What's the use of integral? You fit in a function, get me a number. Okay, I get out a number. So what's the property of this function here? So let's say, okay, you split your domain into two parts, D1 and D2, that intersect at around maybe finitely many point, finitely many curve. Okay, you can also split out the sum. Okay, you split the union of set into sum of integral. Okay, this one we talked about it last time already. So if D1 and D2 do not overlap, except possibly at the boundaries, then the integral split into the sum of integral over each region. Okay, this is pretty important. Pretty important. Okay, you split the integral. You want to integrate over the whole region, you just split the integral into sum. Second part is very important. You integrate over a function 1 over a domain, you get the area. Okay. But you think about it, it is also the volume. Okay. See what I'm talking about. It's also a volume, but it also represents the area at the same time. Right? So let's say, for example, we integrate over a square. Okay, and then we put a surface equals to 1 on top of it. Okay, what do you get? You get a box of height 1. Okay, so the volume of a box of height 1 is the same as the area of the square. Okay, this is quite important. This is how you get the area. Later on, we will upgrade this into triple integral, and then this will represent the volume. Okay, it represents the size of your domain if you integrate over the function 1. Okay, but you can see that this is actually a higher dimension object, right? But the number represents the area. Okay, understand or not? Understand what I said? Okay, so next is, let's say our function is bounded. Okay, bounded above by capital M, bounded below by little m. Then the integral is bounded above by capital M times the area of your domain, and then bounded below by capital small m times area of the domain. Okay, so we can see that this integral respect the inequality. Okay, this is pretty important. Okay, so integral respect the inequality of functions. Okay, do you know why we multiply area along with the value of f? Why is it not working? Wait, yeah. Okay. Yeah. So do you know why we integrate? Why we multiply by the area of the domain? Yeah. You know why? Why? To make it a volume of. Okay. So to make it a volume above the domain. Okay. So so how do you show this? Right? How do you show this? Okay. So what we have first is actually integrate over the domain of, let me write it out. So integrate over the domain D of M of dA less than equal to integrating the domain of f x y dA, and then less than equal to integrating of the domain of capital M dA. Okay, but M and capital M and small m is just a scalar. Okay, so it's a scalar you can pull out from the double integral. What is double integral again? What's the definition of double integral? It's a bunch of sum. It's a bunch of limit of sum. Okay, you have a bunch of sum, a bunch of limit. So you can pull the constant out from the sum and also from the limit if the limit exists. Okay, so we can pull all the way out from the double integral. Then this part here by part 2 is what? Integrating over the function 1. It's just the area of the domain. Okay, so we get m times area of B. Okay, similarly for the upper bound. Okay, similarly for the upper bound. Do you want to see how useful is the bound, or we sure we're going to a new section? Do you want to do this together, or you want to do it yourself? Huh? What you want? What do you want? Do it together. Okay, sure. Let's do it together. So estimate the integral where d is the this with center at the origin and radius 2. Okay, so every time you see this question, right, it's better you draw out the integration domain to get an idea what surface you are integrate over or what domain you are integrating over. Okay, so you have a circle with radius 2. Okay, and then you want to estimate, just estimate this. Okay, so this question is actually asking, can you bound this integral by some number? Okay, so when you see this sine and cos, right, okay, directly you should think about the bound of this sine and cos, the domain here. Okay, how do you bound sine and cos? Sine and cos are bounded above by 1 and below by -1. So if you take the product within these two set of number, you still bounded above by 1 and bounded below by -1. Okay, so all together, the whole function is bounded by e to the 1 and e to the -1. Okay, so now we have go into the setting here. We found a bound for our function. Okay, we found a bound for our function. Okay, by this part 3 here, right, is bounded below by the lower constant, lower bound times the area of the domain, and bounded above by the upper bound times the area. Okay, so what's the next step to bound this double integral here? It is bounded above by 自由, right? Is it 自由? 永志. Okay, sorry, 永志. What is this integral bounded above by? E times what? Okay, 4 pi. That's all. Is that all? 4 pi. So what's 4 pi here? What's 4 pi? Why is there a 4 pi popping out here? What's this? What's this number representing? The area of the disc. Okay, the area of the disc. Area of the disc at the origin with radius 2. Okay, so the area, wow, so nice. I think I also got parcel there. This time, please help me to get over. No, okay. I mean, I'm seriously, I got one puzzle. Okay. Area of the disk at the origin with radius 2. Okay. Yeah. So how about the other side? The other side is e to the minus 1. So e to the minus 1 times the area of the disk as well. Okay. So this is by property 3. Okay. So that's all for this one. So we can bound our integral. I'm not sure you can solve this integral or not. Maybe you can try and solve this integral here. How to integrate over e to the sine x cos y. Yeah, you can try. Okay, after you try, you can let me know. So next, yeah, so this is the recipe to find the special integral. So next we do double integral in polar coordinate. Okay, so when we do polar coordinates, right, our rectangle changes. Okay, our rectangle changes. So in polar coordinate, the rectangle has this form here. Okay, your x and y is described by the polar coordinates now. Okay, and then these rectangles, right, is cut out by the ray that go through the origin. Okay, and then how you connect the 2 points across the 2 rays, you need to use the what do you call that? The arc of your circle. Okay, this is the setting of our polar rectangle. So for example here, this rectangle here, what's the area? Do you know how to find the area of this rectangle or not? Let's say this R here. Do you know how to find it? This should be a typical high school question here. So how do we find this? Any idea? Any idea? Parents? Yeah. Big what? The big square. Yeah, sure. This is the area of the section. Section. Sector. Okay, sector, right? Sector. Area of sector. Correct. Okay, good. So how do we find this cut-off sector here? Okay, so you take the big sector minus the small sector. Okay, so what's the big sector here? So big sector here is b squared theta minus half of a squared. Okay, so all together here we will have this formula here. Okay, so theta here referring to where? Actually referring to this part. Okay, but in our case here, I give you a big angle and a small angle. So this theta here is actually beta minus alpha. Okay, so altogether we have this equation here. Okay, so after getting this equation, right, okay, we can do further simplification. We can combine the radius together and the angle together. Okay, so what is this here? Okay, so we can further split into 3 parts, 3 number. Okay, 3 number here. Okay, I just split the completing the square here. Okay, I just split the difference of square into a plus b and b minus a. So a plus b over 2 here become the radius, the average of radius. Average. Radius. Average of sum of radius. Okay. Average of radii. Okay. And then b minus a is what? Is the change of radius. And then beta minus alpha is the change of theta. Okay. Okay. So our area of this sector here, or area of the polar rectangle here, become these three quantity here. Okay. Okay. Remember from the previously for the rectangle, what we have? We just have the theta x and theta y. Okay. Now we have a special contribution from the average of radius. Okay, this is the difference here. Okay. Okay, so all together, we put together, if you consider all the sum, limit, okay, all together, we have this double integral. So if we integrate over polar coordinates, we have function in polar coordinate multiplied by a extra contribution from R. Okay, and then dr d theta. Okay, so this is the difference between polar coordinate and the rectangular coordinate. Okay, you have a special contribution from the R. Okay, just now I just give you this idea here with why we have this R, but later in general we will see why this R pop up. Okay, it pop up as a Jacobian. Okay, as a Jacobian. Later we will see again, but for now you should remember that when we integrate over polar coordinates, you have a extra R contribution. So in general, this is the polar rectangle we integrate over. Not that we still integrate over rectangle, but this rectangle here is different from the rectangle we considered before. Okay, so these are two different rectangles. But you can see that when the limit go, so when you take more and more partition, right, this rectangle actually converge to each other. Yeah, but in a different orientation, maybe. Yeah. Okay. Can you imagine? Can you imagine when we get smaller and smaller, you are doing actually really close to the real rectangle? Can you imagine what I said? Does everyone know what I'm talking about? I feel like I'm talking to myself again. Huh? So I mean, this rectangle, right? Okay, you can see that this rectangle, when you're taking smaller and smaller polar rectangle, actually it converges to a real rectangle. Can you imagine what I say? Or you don't believe what I say? Huh? Wait. Let me know what I'm wrong. What I say I'm wrong. I mean, you get what I'm trying to say? Or you cannot see what I'm trying to say? I mean, you can ask question. Right. So you can see that this line here, when you get smaller and smaller, actually this slanted line converge to okay. So what I want to say is you can see that this angle here, all angle here should converge to 90 degrees. Is it true? I mean, get closer. You won't get exactly 90 degrees, but get closer. Am I saying the right thing? Yeah.
They are topologically the same.
I mean, of course they are topologically the same, but what I want to say is when you take more and more partition, right? When you take more and more partition here, when you take more and more partition, okay, the polar rectangle converge to regular rectangle. Does that make sense? You try and imagine. You try and imagine. Doesn't you see here? This is actually quite close to a rectangle already, right? Okay, but if you do it smaller and smaller and smaller, it'll converge to a rectangle. So what I'm trying to say is, at the end, two of them are still computing the same thing. Okay, they start out differently, but when you take limit to infinity, they all converge to the same thing. Okay, So that's why we can go from rectangular coordinate to polar coordinate to polar coordinate to rectangular coordinate, and then see which one is easier to calculate. Okay, sometimes one is easier than the other. Okay. Speaking of topology, right? If topology, we just care about holes, okay? But there's no holes here, so they are the same. Okay. Even circle and rectangle is the same. Yeah. We don't care about angle. The subject that care about angle is conformal theory. Okay, conformal theory cares about angle. Those who care about area is called symplectic. Symplectic theory. Volume. I also asked about. I asked about this question to my supervisor. I think this subject is not well studied yet. Wait for you. Why? Wait for me. Okay. Yeah. You can do volume, higher dimensional stuff also can. Yeah. Right. So something invariant on surface. Okay. Okay. Sure. Okay. So, yeah, continue. So try one example. So let's do one example. Let me show you. Okay, this example here. So I want to integrate over the surface. What is this surface here? Integrate 3x plus 4y squared over this area. Okay, the region of upper half plane. You know where's upper half plane? Does anyone know? It's the place where y is greater than 0. Okay. By the circle x squared plus y squared equals to 1 and y squared plus y squared equals to 4. So what are these two circles here? They are radius of 1 and 2. Okay, good. So 1 and 2. So it's the region bounded by these two circles and upper half plane, so above. So we don't want below. We only want above. Okay, so what are these points here? Sure. So this is our region. So this is our region. Can you do rectangular method or not? Can you do rectangular method? Can we do rectangular method in this case? So apply the Fubini stuff. Do you know how to do it if you want to do rectangular method? First decide what's the ds dy you want. So you want to do dy dx or dx dy? Quick decide. Exam time quick decide. Dx dy, okay, sure. Let's do dx dy. So dy, so you need to fix along dy first. So our y's go from where to where? Go from 0 to 2. Okay, go from 0 to 2. How about our x? Our x go from where to where? What happened to our x? X squared plus y squared? Sorry? X squared to y squared equals to 4, sure. And then bounded below by y squared plus x squared plus y squared equals to 1. Okay? But how you split into these two parts here? What's the lower limit and the upper limit here? So lower limit is y minus 1. 1 minus y squared above 4 minus y squared. Okay, that's all. Yeah. Okay, sure. Let's check. Okay, let's check. Let's check is this correct or not. Okay, let's check. Okay, every time we do, we check. So when y equals to 0, what happened to these two limits here? This is going from 1 to 2. So you just go from 1 to 2. How about this part here? How about it? Okay. So let's check again. Where is 2? Okay, where is 2? 2 here is 4. Here is what? Imaginary. For some trouble, right? Okay. So how? So it doesn't quite work, right? Huh? You want to change dy dx. Okay, sure. I mean, okay, so there's some problem here, but I think it should be able to fix, but I'm not interested in fixing now, but you can try. Okay, try fix this. Okay, let me know if you can fix this. I think it is fixable, but we need to do it. So let's change. So Li Kai say, let's try dx dy. Sorry, dy dx. Okay, so that's mean we fix x first. So x have to go from where to where? So there are 4 numbers here. So are we going from -2 to -2 or not? So what's the region you want to pick? Just decide one. Then we'll see what goes wrong if correct or wrong. If you don't decide, decide -2 to 2. Okay. Try this. Thinking what? This one, you mean this one? Okay. So should we proceed with -2 to 2 first? Okay. So from -2 to 2, what happened to our y? What happened to our y? Ming Xiu say what? Split into 4 parts. So many parts. So why do we need to fix into 4 parts? Where's the 4 part? Okay. We split into this 4 part. Why not just split into 3 parts? Just the same, right? Okay. Okay. So you could split into 4 parts. Okay. So 4 parts. What's the difference between these 4 parts? These 3 parts. 袁家. What's the difference between splitting this into this, the integral into this 3 parts? What's the difference? Do you know? Yeah. The below. And then left and right. It's not. Not quite. Okay. Then both of them, all of them are all difference of 2 functions. Okay, but they are of different 2 functions. Okay. So on the first part here, it is going from y equals 0 to square root of 4 minus x squared. Okay. How about for the middle part? Middle part is going from square root of 1 minus x squared to square root 4 minus x squared. And then for the third part is 0 to square root 4 minus x squared again. Okay, so this is the 3 part you need to split into. So actually you can see that this is, okay, actually it's not. Okay, I don't want to say more. But so you can split into these 4 parts here. So let me write up. So you can split into -2 to 1, and then -1 to 1, and then 1, 2, 2. Okay. So what integral you need to prove on y? You need to put a different upper and lower limit as suggested just now. Okay, so you can try and compute this one. Okay, you can try and compute this one. But there's one more convenient way to do it. Okay, what's this actually? What's this whole piece? This is a whole piece of rectangle. Rectangle in a polar coordinate sense. Okay, so we just need to integrate over this fixed rectangle. Okay, you can see that in rectangular coordinate, it's not a fixed rectangle, but when you go over polar coordinates, this become a fixed rectangle. What do I mean by fixed rectangle? Meaning I can use just 4 constant to describe this rectangle here. So do you know what's the 4 constant to describe this rectangle here? So how you describe the point inside this rectangle? How you describe them? So in polar coordinate, you just need to tell me what is the radius and what is the angle. Okay. So what does this point need to satisfy for their radius and angle? Okay. Okay. So the angle is from 0 to pi. Okay. So the radius here is everything from 1 to 2. Okay. And then we restrict to the angle from 0 to pi only. Okay. So that we got this whole region here. Okay. So this is the rectangle we integrate over. So our integrand here from rectangular coordinate to polar coordinate. Okay. So we need to substitute x. Okay, let me include the change of variable here. So x is r cos theta, y is r sine theta. Okay. So we need to sub our function x equals to r cos theta plus y equals to r sine theta. Okay, and then dr d theta. Okay, we still need a r. Okay, we still need an r contribution, correct? Remember just now when we derive the area of rectangle, we need the average of the radius. Average of the radius. Okay, so there's an extra r contribution. Remember when you convert to polar coordinate. Later we'll see that this is actually a general thing from Jacobian. Okay, so so you have dr d theta, right? So over r, you are integrating from 1 to 2. Over theta, you are integrating from 0 to pi. Okay, so you can see that this is a rectangle in the polar coordinate. Okay, remember that just now in rectangular coordinate, we also have 4 constant for the rectangle, right? Do you know what I'm talking about? So let's say, for example, 1 to 2 integrate from 2 to 3 of dx dy, we will have y is 2, 1, and then x is 2 and 3. Okay, but in this case here, our rectangle is a bit different. It is a polar rectangle. Okay, polar rectangle in this case. Okay, so far okay. Okay, so what do you do next? So what you do next is also the iterated integral or the partial integral. Okay, it's also the partial integral. Fubini's theorem also work here. Okay, it's the same setting, but you change variable. Okay. Do you want to finish computing this, or we just leave it as this first? Then later you can check the answer. Can you calculate yourself this integral here? I mean, do you know how to do this integral? You know how to do this integral? So what you do is, you also do partial integral over the variable y first. Over r first, sorry. And then do it over dt. Okay? So whenever, actually, right? So whenever we write this, right, it actually means the iterated integral. So by convention, we already mean this. Okay, so you can do the inner one and then do the outer one. Okay, so there's no confusion here. Where's the confusion? So the confusion maybe comes from the Fubini's theorem. So Fubini's theorem says that you can exchange the integration order if you are integrating over a rectangle. Okay, yeah. So how you do the iterated integral? You treat the other constant as a treat the other variable as a constant, and then you integrate over that variable. Is it clear on how to proceed? Or you want to go through this example fully? Yeah, question. Oh, yeah, over the whole function, yes. Sorry, yeah. So I need to over the whole function. So let's put a bracket here better. Yeah, over the whole function, yes. Sorry. Square the y square, 4y square. Okay, yeah. Okay, I leave out the square here. Okay, yep, that's right. Is it clear on how to proceed? Anna, you want to try yourself first, then you can check the answer. Okay, so the answer you get is 15 over 2 pi. I'll write it out in full in the later lecture notes. I mean, the hard part of this part of multiple integral, right, is how to go from one domain to the other domain. This is the hard part. When you do integration, is similar to calculus 1. Okay, the hard part here is how to find the domain and then how to swap between coordinates. Yeah. Okay. So this is the skill you need for this chapter. Okay. Happy, yeah. Okay, let's do this meme before we take a break. Okay, so let's do this meme before we take a break. So how should we integrate this integram? And how we do this? So where is the polar coordinate? I say I want to use polar coordinate. So how do I produce the polar coordinate? Coordinate would in how many dimensions? 2 dimensions, but here only integrate over 1 dimension. So how to create a 2-dimensional thing? Huh? Y equal to this. So you consider 2 copy of them. Okay, we consider 2 copy of them. So let's call it Y. Call it I. Yeah. So let's consider 2 copy of them. Okay, consider 2 copy of them. Okay, independent variable. Again, independent. So we can combine these 2 using Fubini's. Using Fubini's. Is it using Fubini's or not? Oh, not Fubini's, the other theorem that you can split the 2 independent variables. Okay, so far okay? So far so good. Okay, So what is going on here? So we are integrating over the whole R2. Okay, the whole R2 here. But this is a regular coordinate. We can turn it to a polar coordinate. Okay, so that's why where's the pi popping up here? Okay, so that's why there's a pi contribution here. So what's polar coordinate again? So in polar coordinate, our x will become r cos theta and y equals to r sine theta. So it's how to say? It's reasonable, right? We have two variable in x, y, and then we have two variable in polar coordinate because 2 dimension. You need at least two things to control the value. Okay, so in this dimension here, s squared plus y squared is what? R squared. Okay. Okay, so change to polar coordinate. How is the whole R2 described by R and theta? Then let's change our differential to R times dr d theta. And then our function is e to the minus r squared. So how does this limit change? What happened to my r? 0 to infinity. Okay. How about my theta? 0 to 2 pi, right? So in our R2 plane here, I can describe everything with 0 to 2 pi and then going to infinity in every direction. Okay, I cover everything from minus infinity to infinity and then minus infinity to infinity in the other direction. Okay, make sense? So one of them you look like this, The other you look at the radial direction. Okay, so both of them cover everything inside the R2. Okay, so the problem is, what is this? This is the other meme, isn't it? I mean, close to it. Okay, this is the other meme. So you are happy now, okay, because we produce this thing. Okay, you know how to integrate this, right? Okay, so how to integrate this? Okay, so first of all, so everything here is in theta in r, right? Okay, there's nothing on theta, so we can do the theta first. Okay, integrate 1 over d theta is 1. Okay, so let's use the idea again. So let's split it. So integrate over this. Okay, so integrate over d theta. What do you get? What's this? 1. This is 1 times d. Did you just get 2 pi? Good. Okay. So the problem now is to integrate this improper integral. So just now you said very easy, right? Just use integration by substitution. Okay, so integration by substitution. So use y equal, okay, use the other one. Don't want to clash again. Z equals to r squared, dz equals to r 2r dr. So r dr equals to dz over 2. Okay, so what do you get? 2 pi of integrate from 0 to still 0 to infinity, right? Of sorry, what am I doing? E to the z, okay, over 2 of ez. Is that right? Yeah, agree. Okay, so 2 and 2 can cancel, we get pi. So what's this thing? Minus ez going from 0 to infinity. So this is an improper integral. So really, we need to do the limit thing. Be precise. Okay, but anyway, what's this part here? What's this thing? 1. Everyone agrees 1. Do I need to show 1? No need to show. One of you say want to show, then I will show. Pi times 1. Okay. So what do we get? We get the original function squared equals to pi, which means I equals to square root. Okay. Question? No. Question before we break. You must ask question because this is in your assignment. But I asked you to do triple integral instead of double. Question? Got question or not? Oh, radius. Okay.
How about 3 dimensions?
Yes, later we will talk about it. So you need to be alert. Okay. So, any other question on this strategy? What Yan Bo did also, right? Is this what you did? Okay. Yeah. Yeah, Yan Bo did this in his project 1. Maybe you can talk about this value in the probability. How does it make sense? How is it being used? What is it? What's the interpretation in our life? What does okay? No problem with this.
Is this the okay.
I think this is not because assignment 1 I asked you to do triple integral to solve this. I mean, maybe this is the easiest. You can see that this integral is quite easy to solve. Yeah. I'm not sure if there's more easiest way to do it. More easier way or easier way. Yeah, but I think if you use the normal integration technique for one variable, I don't think you can solve it. Yeah. Any question? Yeah, so in the assignment, I think there's only more work, but same concept here. Okay. How to make 1 dimension into 3 dimension. Okay. Also, you can do 4 dimension if you want, 5 dimension also can. But I don't think we introduce this in this course. So we can do up to 3 dimension. So in 3 dimension, right? Let me spoil a bit. So in dimension 3, let me do a bit spoiler. For a bit. So in dimension 3, there are 2 ways to see it. Okay. One way is you can put a sphere. It's also a version of polar coordinate. Okay. You can imagine a sphere increasing and then you cover the whole R3. The other way is you put a cylinder. Okay. And then you put a cylinder and then you increase in R and then increase in radius. You also fill the R3. Okay. So the usual rectangular coordinate is you put a box. You put a box in R3 and then you gradually increase in all direction and then you fill the R3.
Is it possible to solve?
Ellipsoid, I think can. I think can. But I'm not sure. I haven't write down the change of variable yet. You want to put ellipsoid. Meaning you want to put a watermelon there. Okay, fill the world with a watermelon. Okay. Yeah. Okay. I mean, in principle, you can do this, but whether or not you can write down a consistent way to describe every point, that's the only problem. If you can solve that, then you can do it. Yeah. Okay. Later, we will come back to this again in a precise term. Okay. Okay. So let's take a break until 4, 2, 1.
That's not using a problem.
换的是
哪个？
这边，零到是讲我从因为我 radius 嘛，
Yeah，
从0到无限线这一条线，
Yep
然后0到200的，我每一条线都
就这样转这样子，这样。
做这个转换的时候不用表达，不用写东西的，是不是？
technically 是要，但是我看到这个 call 是不是他们全部就是画一下图啊就讲了，画一下图啊就讲了，而且这样吧
因为通过定律来计算。我发现到只要是这本书没有提到，应该就是热能现象。
actually 嘞，actually 等一下会 touch 到，就是 change of 就是什么 transformation 啊，其实就是 transformation 有看一下，然后之后会看到 actually 其实是叫做这个 transformation change of variable in multiple transformation one to one 的 transformation。real analysis 只是 care about real number。对，所以它叫 real analysis。还有一个东西叫 complex analysis，就要做
可是他们讲
complex。
complex 的比热能容易，
对，因为什么呢？最难的应该都要在 real 那边解决。complex 的话比较 straightforward。还是他们没有，可能他没有被挖到这样多东西，我觉得也是可能的。但是complex 有一个好处就是 complex 是一个这是一个很
完整的。
也是完整，所以它好像怎样讲呢 complex 啊，
那么一般去 complex 的话，基本上就是上面就是讲你有入了，你已经是什么都能找到了。
其中一个，那是其中一个，
入的话有洞，因为有些不懂找不到。
对，OK，这样子讲的话，你应该是指那个方圈变得容易看去，因为你看我们现在的 square root 啊，又不可以那个地方，等一下 long 又不可以那个地方，可能放去那个哪里啊，放去 complex 的时候呢，我们所 consider 的方圈呢就变简单多了，因为做什么呢？因为你 long 里面啊又不可以放 complex，什么叫做 long complex？这样它就放一个 length 方圈在里面，放 length 方圈进去，那就是跟普通的 r 一样了。应该是这样的原因因为 complex 你可以 order 它吗？应该是可以 order 吧？
好的，
就是比如说 real number 你可以 order 嘛，就是第一个比第一个大，第二比第二大，第三比第三。real complex 应该也可以 order，不会 order 吗？
记得有时候要一大一大画个角，
是
但是一大一也不可以小。
OK，这样就 OK 了。
除非你 define length，你 define length 就可以了。
你 define length 的话，这样就变成一个 polyset 啊，就这样。因为有些人要一样的嘛，很多人要一样的，在一个圆圈里面的人都要一样。对，
换那个，x y 换去其他的。
什么原因？
就是我理解，可是我在那边想，需要不要写那个？为什么会这样子？
应该是要的，应该是要吧。
我就画图了。
现在就这样啊，现在就画图，现在就画图。
一个人讲一个都已经很多到100到很多。
这样
最前面这个
那个
这一个为什么可以这样可以建成X，可以是2个
没有关系的一个 bro。
对，
什么叫为什么？就是这个是一个 dummy variable 来的，就是我要换成什么都可以。我可以换成 z 也可以了，可以什么东西都可以。但是我这里想表达就是这两个是没有关系，就是两者是 independent。但是 independent 就是一个我是 over 一个 real line，另外一个 over 另外一个 real line，然后把这两个 real line 乘在一起过后呢，我可以合在一起。这个合在一起的原因其实是有一个原因的
哦，是吗？
啊，那个原因前面那个原因。然后合在一起过后呢，这个才是这个 polar coordinate 的精髓，就是你 integrate over 那个 rectangular coordinate，其实就是integrate over 那个polar coordinate。其实我们没有认真解释为什么你可以这样子跳，但是后面会解释。但是前面我只告诉你，假设你可以把它看成 polar coordinate，这样你就可以开始用 polar coordinate 来写。
然后一个就是这个地方
呀，
就是这个
对
这个函数 S
对
乘以这个 R
对
是什么意思？
没有，这个 R 是跟着这个 differential 一起来啊，它跟这个哦，你是说你是说它为什么出来，还是为什么乘它，还是它就是一个 function，它就是一个 function，它是这样子看，
但是感觉从几何意义上来，
几何意义啊？
如果 F
对，
因为你这
对
个里面表示的是一个
改变 R 的改变跟 angle 的改变，
就是就这一块小
对，
的
没有错，
这样，
没有错，
它乘这一个是
对，
就是要把它放到一个 three dimension，
推这么下啊，对，然后
它乘这一个它是怎么
它
变化的？
长度被 R 改变，你知道吗？
对啊，它
对，为什么这样呢？为什么呢？你要知道为什么，是不是？因为你看我们的那个，它其实不是在指，诶
不应该是一个类似于
啊，
勾股定理，然后就是要知道一个这台 x 得到 y，这台 x 贝尔那得到 y 贝尔这样的一个形式，
我不在你讲，
就是它是到这个 origin 的那个
origin 的 distance，
对，就是它这个生成的这样的一个就是
可是那是 domain 呢，
对，懂了。
我想想啊，给我看一下啊，
那求长度就是用那个distance，就是得到 y 的 square 大于的 z square。
其实它指的改变应该是改着它的那个 area 耶，是它的 area 的改变，其实。它是因为之前我们是 integrate over 这一圈东西，但是现在是一个长这样的东西，对吧？像其实这个 R 的 contribution 是为了说这个应该，如果我没有错的话，等一下我们会提到之后，就是如果你们有学过 linear algebra，说那个 area 是用 determinant 算出来的话，我觉得应该它控制的是这个 area，它控制的是这个 area，而不是它的这个。它控制的是这个 area 改变。你看，你 integrate over 这个 area 跟这个 area 是不同，你懂吗？
我懂，好像你
啊，所以你呀
来看一下。
啊，
刚刚讲 open set close set 的吗？
差不多要开始了。你要看我的 note。opposite close set 要看我的 note。Okay, we should start soon. Okay, so you see, my assignment involve open set, close set, bounded set definition. So you need to look for my lecture notes because the original lecture note doesn't have this. And also, I think the textbook also doesn't have much, so you can only rely on my notes. Okay, so you must read my notes. Okay, remember I said lecture notes is the Bible of the course. Okay, so you need to rely on the lecture notes. Because I can change to whatever is related.
So you are Jesus.
In this course, I'm a Jesus. Okay. What should we do next? Okay, we do this cylinder, rectangle. How about should we do one more? Do one more? One more polar coordinate integration. Do you want to do one more example? Let's do one more example. Which one is more interesting to do? Hey, my screen gone. Which one is more interesting to do? I think both of these have some technical content. Okay, how about let's do how about do rows first and then later we also do the other one. Okay, let's do this. Use the double integral to find the area enclosed by a loop of 4 leaves. Okay, of this. So what's the function you need to integrate over? What do you think? Huh? What's the function you need to integrate over? The question asks for area, not volume. So how? Don't know. Straight away, give out already. Think. Where do we connect area with double integral? Double integral of 1. Okay, good. So double integral of 1. So let's write down. So you want to find an area of a region, you need to integrate over the region with the function 1. Okay, good. So next, you need to determine your integration domain now. So you're just finding a loop of the 4 leaf rows. A loop of a 4 leaf rows, which means a leaf. Okay, we integrate over a leaf. So this leaf here is controlled by the radius is controlled by cos 2 theta. Then let's write down. So this leaf here is controlled by r equals to cos 2 theta. And the theta here is going from minus power 4 to power 4. Okay. Okay. So what's your integration domain? Okay, obviously now this is in polar coordinate. We want to use polar coordinate. Okay, double integral in polar coordinate. So in polar coordinate we have r dr d theta. Okay, so just now Li Kai asked about this r here, right? If you multiply r to your function, does it mean by you increase your function or not? Okay, so later we'll see that this r is coming from determinant. So you see last time in linear algebra course that determinant will represent some area, right? Okay, change of the factor when you change the area. Okay, so this actually, I think, so is representing the change of area of a rectangle to a polar rectangle. And you can see that obviously these two are different, right? Okay, so there's a difference by this factor r. Okay. Okay, so what's the integration domain in this case here? So over R, so we will integrate from where to where? 0 to 2 theta. Okay. First, you fix your theta first. Our theta is minus pi over 4 to pi over 4. And then how you control your R? Exactly using the graph of the rows. Right? So you start from 0 to cos 2 theta. Okay. Okay. So this is like a degenerate rectangle. Okay. Degenerated rectangle. So these two parts got stick together. Okay. Yeah. So how do you integrate this? There's no contribution from theta. Okay. So you integrate over R first. So you get R squared over 2 from 0 to cos 2 pi dr, d theta, which is just 1 over 2 cos square 2 theta. Okay. So what do you do here? You cannot integrate cos square, right? So you need to use the what? Trigo identity. What's the trigo identity? What's the trigo identity? I think you cannot integrate over 2 theta, right? Which one? Which one you cannot integrate over? Square or the part or the square, right? Okay. So what do you do? What's the formula you need? What is it? So what is it? I think something divided by 2, right? 1 plus cos 2 theta. This one? Okay. Okay. I believe you. So 1 plus cos 4 theta over 2. Okay. And then you can do the integration. I think you should get pi over 8. Okay. Okay. So far, okay. 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 Next, find the volume. Okay. Let me tell you, the part of this question is always finding the integration domain. So make sure get the integration domain right. Otherwise, you will get wrong answer. So find the volume of the solid under the surface z equals to s squared plus y squared. Okay, this question asks about volume of the solid. Okay, under the surface s squared plus y squared. So this surface should be always positive. Okay, so you just compute the double integral, it will represent the volume because this surface is always positive. And above where? Above the xy plane and inside the cylinder s squared plus y squared equals to 2x. So you need to check where they intersect now. Okay, so where are they intersecting? So what's the cylinder here? S squared plus y squared equals 2x. So on this cylinder, right, what's the base here? This is actually a shifted circle. Can everyone see this? So this is actually x squared minus 2x plus y squared equals 0. Okay, so you need to do some shift completing the square to see that this is a circle, the unique circle, but base at 1 and 0. Okay, the center is 1, 0. Okay, it is drawn here. Okay, I think you should be able, can you? You can probably try and find this using rectangular coordinate. Maybe you can try. Yeah, try with rectangular I feel like I don't know how to spell this rectangular Is there something wrong? Oh, right, R is C. Okay. Rectangular coordinate. Okay, try find this using rectangular coordinate. You know how to do that? You know how to do that? You know how to split this region into rectangular coordinate? So depend on you want to do dy dx or dx dy, right? Okay. So let's say we do dy dx. Okay. So I need to fix x first. Okay. My x is going from 0 to 2. And then how I control the y? How I control this y? How do I control the y? 原加. How do I control the y? If I want to integrate from 0 to 2. What's the lower bound of my y and upper bound of my y? Huh? Quick. Any idea? Any idea? No idea. Okay. No idea. Tishon? What's your lower limit? 2x minus x squared. Oh, okay. Or you use that presentation. Okay, sure. 2x minus x squared. Okay, good. So upper limit should be positive 2x minus. Okay, yeah. So you can compute in this way. In the other way, we can use polar coordinate. Okay, we also can use polar coordinate in this case. So you should try this. Okay, you should try this and then check with polar coordinate answer. So what is the polar coordinate I meant here? So let me write down what we want. Okay, we want to do this integral here over the polar coordinate r dr d theta. Okay, so we use the same change of variable like just now, what we did for the integral of e to the minus x squared. So we have x equals to r cos theta, y equals to r sine theta. So x squared plus y squared is just r squared. Okay. So how we determine our theta and radius here? How we determine our radius and theta here? So theta is outside. We want to fix theta, fix theta first. Huh? Where's our theta? Where's our theta? You want to integrate over this circle here. Okay, where's our theta? So this really depend on how you write this circle here. How do you write this circle in polar coordinate? Actually, we learned this when we try to sketch the limacon. 0 to? Why? Why not to 2 pi? Okay, yeah. So after 2 pi, okay, if you use this representation here, after pi, the shape repeats. Okay, so meaning you only need to draw 0 up to 2 pi, you will finish the whole circle. If you do pi to 2 pi again, you will multiply the value. Okay, 2 times the value. So you just need to multiply from 0 to 2 pi, 0 to pi. Okay, so let me write down the domain. So what's our domain here? So R is controlled by the how you parameterize your curve. Okay, let's just parameterize the curve using 2 cos theta. This is what we learned last time. Okay, the limacon. And then our angle is from 0 to pi. 0 to pi. Will we have trouble 0 to pi? I don't think so. Let's try this, okay? Try this. Yeah, try at home. Okay, you try at home. And then you let me know. Okay, try this integral here. And then what we should get is 3 pi over 2. Okay, you try and compute this at home. Okay. Is it clear what you to do? Okay, so you try at home, check whether it's 3 pi over 2 or not. Then let me know. Okay? If not, let me know. If okay, then we can pass on. Okay. So before we go to triple integral, any question on this polar stuff? Explain. From the whole thing, everything. Okay. So the question, what's the question? Okay, the question asks about volume of a solid under the surface x squared plus y squared. Okay, x squared plus y squared, is it always positive or not? Yes, right. Okay, so that means the double integral of this surface represent the volume of the solid. Okay, so we need to compute the double integral of the surface. So where does this volume lies? It is above xy plane and inside the cylinder x squared plus y squared equals to 2x. Okay, so represented by this picture here. So you need to find what's the integration domain to integrate over for this solid here. Okay, so meaning you need to find what's the base, right? What's the base here? Okay, so to find the base, you need to look for the circle that define the cylinder. Okay, right? So you need to find the base of the cylinder here. You know how to find the base of the cylinder? How to find? So how to find the base of the cylinder? Actually, this equation here is the base of the cylinder. But why does this trace out a cylinder? Good question, right? Thank you. Okay, so why this trace out a cylinder? Because this equation here is an xy variable. Okay, this equation is an xy variable. You want to draw this circle in the R3 dimension, right? Okay, the space of R3, 3-dimensional. So in every Z, you maintain this circle here. So that's how you get the cylinder. For every Z, you have this circle. That's why in R3, you trace out a cylinder. Make sense or not? Depend on what space you look at it. Okay, depend on what space you look at it. Remember just now I start the class with by talking about 1 over x here. So 1 over x in 2-dimensional is just this curve here. But if you consider this surface, this curve in 2-dimensional, okay? I mean, function of 2 variable, you need to draw it in 3-dimensional, right? So you will have this surface traced out by this curve. Make sense or not? Because why? There's no contribution of y. I mean, there's no controlling factor of y here in this on the right hand side. So that's mean for every y, you have 1 over x. Make sense or not? So for example, f of x0, you got 1 over x. F of x1, you got 1 over x. F of x minus 1, you also get 1 minus line. So every y, you have the same line. So because real line is complete, is like is dense, is all the adjective I want to use, is continuous. Okay, it's not precise, but I mean for every y you have this line. So when you see this line close and close enough, right? So they will form this surface here. Surface formed by this 1 over x. Make sense or not? Line. Yes. 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 Yeah. So in this case here, you got a circle, right? But why is it a cylinder? Because you consider this circle in a you consider this function in the three-dimensional case. So where's the z contribution in this circle here? So no factor controlling z. So meaning every z you have this circle. So that means you have the cylinder, because cylinder is made out infinitely many circles. Okay. Yeah. So you need to be careful about this. Yeah. Okay. So yeah, when they put cylinder, that means they consider it in 3D, three-dimensional. Yeah. Color the volume. Okay. I will try my best. Color the volume. Okay. Because in this picture here, right, you can see that actually the part that you want to find is covered by this cylinder already. So meaning you need to look through the cylinder. You need to look through the cylinder. Okay. You don't know which one? Okay, good. So let me draw it. Hopefully my drawing skill is good. Okay. So can you imagine? Okay, first imagine the intersection of cylinder with this object here. Try imagine it. You imagine first, and then see I can draw it or not. So I want to draw it. So it is about. Okay, let me turn this. Hey, sorry. So let me turn this. So let us face this way. Face this way. Okay, face this way. So I will get something like. Okay, let me use my imagination. So something like this. Yeah or not? So let me draw again. So something like this. Okay, so your intersection will look something like this. Okay, can you imagine? And then, but this part, right, is facing up, slanted. So it's like this, like this part. So slanted already. So you want to look for the below part, the part that below it, below this purple. Can you imagine? So imagine this purple, how do you call this? Eclipse. This purple eclipse, right, facing you, but slanted like this. So there's something below it. So you need to find the volume below it. No. This is the definition. This is what we want to find. This is, you see, this is the question. Under the surface. Under. And then the definition of double integral also give you under. There's nothing above. Above is infinity. Right? Only below is bounded. Because you bounded by SY plane. Okay? Bounded by SY plane. Okay? So you got like this. Like this. But this one is a eclipse. And then below is a circle. So under it. Okay. Looks very well. You get it? Okay. Okay, yeah. I mean, this topic, right, you should be able to imagine, but if not, you just calculating something that you don't know what is it. Okay, just do the double and triple. Yeah, it's not.
How to imagine it?
Okay, I mean, sure. I mean, okay. Okay, I mean, okay, sure. There's some remedy to this problem. Either the question is very easy to understand, okay, then you just do what you need to do. Second is maybe we'll give you some easy. Okay, one possible way is to give you a figure. The other possible way is give you simple diagram. For example, plane. You should recognize, right? Plane. Okay, and This one maybe you don't recognize, but the other class they should recognize because they learn conic section. You guys don't learn. They took it off from the syllabus. I don't know, but they learn it, so they should recognize this is one of the quadrate surface. So they should draw this parabola. I mean, should be able, but of course, I know a lot of them don't know how to do it. But how to say? The other thing I say here, right? I didn't refer to this picture just now actually when I explain it. What I explained is, see, this surface is always positive. If it is always positive, then you just do the double integral. That's all. Yeah. Okay. Yeah. So if the surface is always positive, then the double integral will represent the volume. That's all. This is the line you need. Yeah. If you cannot see this picture, also never mind. And so you need to check whether which part is positive, which part is negative. If it is negative, then you need to take the negative of that double integral, so you get positive. Remember last time we got the double integral that cancel out by the positive and negative volume. Yeah. Yeah.
So if you have negative, that will be easier.
What do you mean?
The case have negative. So here will be easier to see, easier to observe.
Why? Why you say so?
Because we can't directly, if negative, we can't directly do the without immediately without drawing out.
So why does it negative will make it easier? So why negative make it easier?
I think negative make
Oh, yeah, 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 yeah. Yeah. Sure.
so the complicated or maybe you will say that this positive and then you can apply to PV like this.
Beneath doesn't care about negative, positive. Only volume we want positive, negative. Houdini just care about continuity. If it is continuous, then you can exchange the order of integration. Only volume we care about positive, right? We don't want to have negative volume, right? It's actually the same as the area problem. Does the integral represent the area under the graph? Yeah. If different, if you get negative, then maybe you need to introduce negative to the integral. Okay. You mean this one? You mean this one? Okay, this is, we are trying to do this using rectangular coordinate. Oh, wait. So what am I doing now? 2x minus x squared, huh? Okay, so this 2 come, try to be naughty. So make it up. Okay, yeah. Yeah. I mean, I what I'm doing, I'm just parameterize this domain here. Okay. Yeah. I mean, you can compute two ways and then see if you also get 3 pi over 2. Okay. Compute the rectangular way, compute the polar way, see if you get the same answer. 3 pi over 2. Okay. Okay or not? Okay, good. Okay, let's go through some definition before we take a break, okay? Let's go to the next definition. I mean, yeah, break until Friday. Okay, so next is this the triple integral here. So for triple integral here, we no longer dealing with rectangle. Wait. Yeah, we no longer deal with rectangle. We deal with boxes. Okay, rectangular boxes. So rectangular boxes, you have three sides to take care. Okay, not just dx dy, you have dx dy dz. This is referring to the domain of your function. Okay, your domain of your function becomes 3D now. Okay, that means your graph has to be in 4D. Okay, but 4D we cannot draw it. We cannot imagine. Okay. So if you can imagine 4D or draw the 4D, then maybe you'll become billionaire now. Okay. Everyone is looking for R4. What's your what's TikTok? Okay. Okay, cool. Okay, so triple integral here also defined by three sum, three limit, okay, over x, y, z. So the picture is here. So this is the whole boxes, and then when you take limit to infinity, you are cutting the boxes into infinitely many boxes. So infinitely many boxes, and then become a point in the end. Okay, and then you fill up all the space under the curve. I think that's all I want to say today. I'll say, okay, you also have Fubini's theorem in this case here, iterated integral. Okay, do 3 times. Okay, you can swap. When can you swap? I think you can do it only inside the box. Okay, I think the condition should be the same. If f is continuous at the box B. Okay, and then within the box you can change your limit. Okay, what do you mean by change limit? Have you think of it before? So it's like you cut it on the x direction, smaller into strip, and then you cut the other direction into strip, and then you cut the other direction into strip. So it doesn't matter you cut which direction first. Make sense, right? Okay. Because in the end, you still get all the point inside the area under the graph, or the region under the graph, volume under the graph. Okay. Okay. So now we no longer call it a volume because it's a 4-dimensional stuff. I think the textbook call it a hypervolume. Yeah. When it is higher than dimension 3. Volume what? Volume domain. Why? Why? Volume domain. Oh, the domain. Oh, okay. The domain is a volume. Okay, sure. Yeah. The domain is a volume. But I mean the triple integral is a hypervolume. Yeah. Yeah, the domain become volume because domain live in 3-dimensional now. Okay. So yeah. So hopefully we will end this section. I think not possible to end. I'll try end it before this Friday. Okay. So I will see you on Friday. This Friday.